Okay.
Yeah, I can hear you great.
All right. Let me see if I can share my screen. Okay, so if I go into full screen mode, do you see full screen?
Yep.
Sure do.
Perfect. Okay. All right. Well, good morning, and thanks for inviting me to make a presentation. This is our heliophysics package, SciPy. And although I'm the one that's speaking, David Stansby, who most of you probably already know, did most of the work developing the package. Unfortunately, he's moved on to more general programming now at the ARC Center at UCL, but he's still working with us on the side, but we've started to take over the development of the project. So what is SciPy? It's simply a package for loading and visualizing the output from our global MHD runs. We have one particular model, mass, and so it's tailored to reading in those results. And they are somewhat unfortunately in HDF4 or now H5 data format, and that's on a staggered but uniform mesh. So that makes it difficult for people to use our data as much as we'd like. And because all of our data is available on the website, it's proven challenging sometimes to get people to be able to interact with the data. We're also using an astrophysical code called Pluto. It's also an MHD code with different different bells and whistles, including a much better shot capturing algorithm. So SciPy will also support that data, but it turns out that data is a lot more easily read in anyway. So why do we need SciPy? Well, primarily, I think the scientists at PSI and me in particular have been transitioning from various commercial software packages to Python. I made the switch to R for a lot of my analysis a long time ago, but I couldn't convince the others. And since Julia hasn't really caught up enough to be a viable option, at least for us, we agreed as a group that Python would be the best compromise. But we also wanted to create a package that would also allow other scientists in the community to be able to use our results without either dumbing it down, which you might see in a web-based portal, which we have. But that just allows you to click through various pre-designed visuals. Or the alternative is to give them a much more difficult code, give them snippets in Fortran or IDL or MATLAB so that they can load the data. So the main initial goal was to provide something that was an easy way to get the data into Python and then provide some basic visualization tools to get them started. And of course, when I say they, I really mean me too. So this is something that it's only going to work if it works for me and the rest of the people at PSI, because I think then we will be invested in the ecosystem ourselves. So on to some of the motivation for the types of things that we wanted to create. I'm showing here a visual summary of some of the types of data products that we create. And they range from simple time series analysis that you can see in the bottom right-hand corner, where we're comparing ACE data with the MHD model results. In the top right-hand corner, you can see that there's white light comparisons between model and observations, and EUV as well at different frequencies. And all of those are created as a post-processing exercise after we've actually run the mass calculations. We can also do slices in various planes, depending on whether or not we're looking at the corona or the heliosphere. Different emphasis can be made on the type of structures that we're looking at, such as the solar wind, the Parker spiral that you can see in the bottom center. And we can also create products that you can't actually measure directly from the data, such as magnetic field lines. We can draw those in various planes, and in terms of being able to do a topological analysis, that's a very, very robust way for us to do that. We can also calculate some more complicated parameters like the squashing factor that you can see in the bottom left-hand corner. and they allow us to look at topological issues related to the field. In particular, you can look to see where the likelihood of the field undergoing reconnection might be taking place. So they can be quite powerful. So as a minimum, we wanted to be able to support us and other users being able to create these kind of graphics, not necessarily all at the beginning. So to give you a very brief overview of the Psi package, the requirements are very minimal. You just have to have Python greater than or equal to 3.7, and obviously you need the HDF libraries as well. The installation is very simple, and it should take care of all the dependencies that are necessary, like AstroPy. All the code is written in Fortran. We just added a Fortran tracer, and as we go forward in the future, we'll probably add quite a bit more Fortran code, because that's the way we developed our tools, and it's also probably much more computationally efficient to do it that way rather than recoding it in Python. We use the restructured text RST system for documentation, and the package is available on GitHub at that URL. And I'll just, oops. I guess I'll paste those in the chat after I'm out of full screen mode. And you can also read, the documentation is on Read the Docs. In fact, if you just Google SciPy, it comes up, I think, as one of the first options. It's released under the MIT license, which is the most permissive I could find. If any of you have more experience with the licenses and guidance, that would be great to hear about. But I'm very happy if we stick with the MIT license. So to install SciPy, the easiest way on a Mac is just to use Conda to install the HDF4 libraries. You can use apt-get on Linux, and then the actual installation is just a pip install. And if you want the bleeding edge, then you can just do the 3 commands at the bottom here. I would advise against doing that. I did that on Friday just to update things, and it broke the new field line tracing routines that we have. So at the moment, if you are going to play around with this, I'd stick with the official release. So the core features that we decided on at the beginning were that it should load the model data sets, obviously, and that it should provide basic unit conversion. So our code units are very obscure, and I don't think that the general user should have to remember 481.37 is the conversion from hour velocity to kilometers per second. It should also be able to interpolate through the data cube or a data sphere in our case. It should be able to do 1D and 2D basic plots that are sort of the bread and butter of publications. And then I thought it would be nice to be able to do some volumetric plots. We also would like to provide the capability of tracing magnetic field lines, because it's a staggered mesh and it's non-uniform. Makes it a little bit more difficult, especially if you're trying to be precise, because especially with null points, small errors in that tracing can rapidly diverge in the heliosphere. And we wanted to provide some case study examples, so comparison with in situ measurements, and then comparison with remote solar observations like the white light and the EUV. And also to provide derived quantities. Again, because of the staggered mesh, it's not that straightforward to be able to compute things like the alphane speed or the plasma beta or entropy, because they're all on slightly different meshes. So we wanted to take care of that. And then there were various other things that didn't make it into this kind of core feature set. So what we've actually done is in black, what is partially working at the field lines, and what still remains to be done are highlighted in red. So here are some examples. We can go through them in a bit of an interactive session in a second, but just in case that didn't work, I just wanted to show them on a single slide. So the time series comparisons, this shows a comparison with PSP observations. It's not a particularly good one, but that's the one we used as our test case. And then on the top right, you can see a cut in the meridional plane that shows the radial velocity on the left-hand side, and then the density on the right. And a nice feature that we added was to include a renormalization method, so that you could take a variable and just dot this renormalization method onto it, and you could give it a power of some integer, which is really nice. So in this case, density is scaled by r squared because of the radial fall off of the density as you move out from the sun. But other parameters like the magnetic field might fall off as 1 over r if it's the transverse component, or 1 over r squared. So it makes a nice way to make the visualization look reasonable. We can do slices in a spherical plane, and slices in the equatorial plane. And then finally, in the bottom right-hand corner, before I upgraded my version of it, you could draw field lines from some reference sphere outward, and you can see this is going out to 60 solar radii, and you can see the Parker solar spiral is starting to take shape. Okay, so I'll run through a couple of examples to show how you create the plots that were on those previous pages, and then I will briefly summarize. So now let me see if I can stop sharing and then reshare. There we go. Okay, so now can you see a Python session?
Yep.
Sure
Great.
can.
Okay, and hopefully some of this is visible. Let me see if I can move this over. Okay, so here's the first one where I'm just comparing a time series, and it just illustrates these are the packages that need to be installed. We provide a sample data set so that you don't have to start by downloading the data from the website. Ultimately, it'd be nice to be able to provide a more abstract summary of the data, the model data that you want. So perhaps you provide the Carrington rotation, and then it will go to our website and it will list all the various solutions for that particular Carrington rotation. You can pick one of those, and then it will pull the data as necessary. But at the moment, if you want to look at something specifically yourself, you have to download the data and then you point it to the data, which is very similar to what we're doing here, setting the mass path variable. But in this case, it's actually getting the data kind of hardwired. So now that we have the model data, we want to grab the PSP data. So when we started this project, we were still using HelioPy. David has since said that it's not supported and that we would be better off using a different package. So I've started to look at PySpeedus as the alternative, which I think will probably serve our needs as we go forward. Then next, just grab some of the ephemeris data. And then this is sort of I think one of the most important steps here is to actually interpolate the model data onto the actual coordinates of the spacecraft. So that's what's passed in as the arguments here to this sample at coords method. And then once you have that, you've got the observed data and the model data at the same location, and then you can just plot those two results. And we get this plot, and everything is taken care of. Now you've got control over the labels and things like that, but this is the way that the default way it's set up to present that information. So that's a time series example. Another example is to do a slice. So in this case, we'll do the same thing that the variables have already been inputted anyway into this session, but that works again. And then here's the renormalization. So we're going to plot the number density, which we call rho in our simulations, but it's not a mass density. And the radial underscore normalized with parameter 2 just scales everything by r squared. And then we'll pick a particular index from the simulation that we're going to make the slice. And then we'll plot those results for the density. Okay, so that density is not being renormalized. And then the red line that you can see over the top is the heliospheric current sheet. So that's just a contour with a level of 0. So it's the line where the field BR equals 0, which is something that we often plot. So it's useful to do. And then here's the output from when you actually renormalize the number density. And now you can see all the structure as it moves out. You can see these interaction regions. And then this one is basically the same type of an example when I'm thinking about it. So in about 25 lines of code, you can read in all the data and you can produce a plot that looks like this. There's an issue here that the character sizes are a little bit too large. So I need to take care of that. But otherwise, this is something that would be fairly complicated for somebody to be able to do. And I think if this was in a Jupyter notebook, it would be even more straightforward, because then we could make all the comments going through that. The last one was supposed to be the most appealing, because it was going to draw all these field lines. Unfortunately, this is what happened when I tried it on Friday afternoon. So there's definitely a mistake here. And unfortunately, even though I can go in and look at the code myself, David wrote this, so he can probably guess where the error was introduced and probably fix it very, very quickly. So that's sort of it in terms of the examples. It is undergoing changes from week to week, so we hope to be able to add a number of new features to it. And I will just go back to those slides. Let's see. There we go. So some of our proposed updates to implement a more sophisticated field line tracing routine. At the moment, it just draws the field lines in one color, but it'd be nice to be able to have an option to draw closed field lines in one color, open field lines in a different color, and disconnected field lines in a third color. Or to be able to do something even cleverer, like TechPlot, I think is one example that does this, to put a variable on the field line. So maybe have temperature. Actually, it would have to be temperature renormalized by multiplying by R or something to show how that evolves along the field line. We're also looking at PyVista as an upgrade to at least supporting 3D visualization. It seems very promising, but we haven't put anything yet into the code. And I'm not sure whether or not, and I guess I'll come back to that, whether or not it's best to incorporate that into the core features of this package, or just to provide examples in, say, Jupyter notebooks. And as I mentioned earlier, being able to incorporate all of the things that we normally do after a run completes, I think would be useful. So squashing factor, which I mentioned earlier, the location of coronal hole boundaries is straightforward for us to do once we have the magnetic field geometry. To be able to create the simulated white light and the UV images, they're calculated by integrating along the line of sight either the density or some functional form of the density and the temperature, and then being able to compare those directly, say using SunPy to see how well the model does with the observations. And then also to be able to calculate other variables like wave speeds, plasma beta, things like that. So that's it in terms of the package itself. I'm happy to take any questions. I find it really useful, though, to ask you some questions too. So if we have time, and maybe after the second presentation today, some of the things that I think you'd be able to help me with are the questions that I've listed here. But I'll stop here and see if there are any questions or comments.
If there aren't any questions or comments, we can go ahead and go through Brian's presentation and then come back to these questions that you have for us, Pete.
Sounds good.
Brian. Oh, go ahead.
Hey, no problem. My slide deck is on the NASA environment, so I will be very happy to share it. What actually might be best is because I've stopped getting the environments to allow the emails to the, so I'm supposed to get a request email to share it back to whoever's requesting it, but I've stopped getting those for whatever intentioned reason NASA IT has. So I can't, but I can specifically allow people, and I've allowed Julie. And Julie, if you don't mind downloading the presentation as a PDF and then disseminating that to the list,
Sure.
Probably the easiest way to get it to folks. In true form, I have only just finished editing it. So I am now going to present this freshly assembled deck. So let's do that. And slideshow, I don't want that. Okay, there's that. Oh, I see. I have to share my whole screen here. How do I share? Share screen, share the whole screen, sharing the whole screen. And now, okay, so I'm way ahead of myself. There, can everybody see that?
Yep.
All right, fantastic. Thanks for having me over to this. Longtime admirer and of the PyHC project. I think there's a lot of great stuff here. I'm here to pitch to you all a way to make things even better. It's sort of peanut butter and chocolate proposition, if you will. Two great tastes that taste great together, or something like that. So it's about a shared software environment for heliophysics software. That's you guys. And I want to basically give you some background on what our team has been doing in the HelioCloud project and how that impacts you guys. So here's the motivation on a single slide, if I can. And that's the HelioCloud project. So what is it about? It's to create a working, stable environment. Our primary target is for PyHC, but also some other research software that heliophysicists might use. We have incorporated IDL, for example, but PyHC is the main focus for us. And we want to basically create a container in which this runs. Right now it's Ubuntu 20 that implements this Python environment sort of as a default Python environment. And what that'll do in its final form is provide a cloud-based platform called HelioHub, if you will, which is using this backend container. There are actually three forms in which this is anticipated to be distributed to the public. First, basic one is software configuration, software package config. So essentially that's conda and environment.yaml file. So that others can create a virtual environment on their local machine. And it's all the engineering that needs to go into the dependency, conflict resolution, et cetera, has already been done. So they don't have to worry about that. So problems like making PySpeedS work with Happy are not an issue, although I don't think those two are in conflict or anything like that. But we have found in our work that there are some minor third-party dependency problems. I won't call anybody out per se. We've worked with the individual maintainers to work to resolve these. And you know, in the process of doing that, we realized that there's some virtue to be had here, because when we, as is currently going on, when we sort of develop in a stovepipe and we choose the third-party dependencies that work best for each of our projects, it presents problems for the downstream user who might want to use more than one PyHC package, right? Because when those third-party dependencies are in conflict, then they have to visit dependency hell and do the conflict resolution. It just makes sense from my point of view that we do this up front and that we all get on the same page with the third-party dependencies that we want to bless. And I'll get into advantages of that, but in a later slide. But I'll just leave you with that to be thinking about already. So at any rate, the basic form is a Conda environment file. We also intend to distribute containers which pre-build the Python environment, the Conda environment, so that it, as a default, when the user logs into the container, it's there. It's up and running. That's the environment that they work with. They don't have to build a new Conda environment. It is the virtual environment they start with. It's their user container, so they can go ahead and muck around with that as much as they want. And if they totally hose it, they can always go back and rebuild the Conda environment because they have the Conda environment file. Also, this container should back a browser-based analysis environment. We can see this being distributed in terms of our initial thrust right now is to implement this on the cloud, but we can also see and have work on the books for the next fiscal year to implement that on top of on-premise large compute resources that we have at NASA. We could see others doing it. And so essentially a very easy on-ramp to not only using the cloud for heliophysics research, but also high-end computing or HPC resources that might be at various partner institutions. This environment we've been calling DASC Hub, and I'll show that in a bit. So the characteristics of all of this is that we want to be public and open source, and we are. We want these items, these forms that we're distributing to be extensible by the users. In other words, they're a starting point. They're a safe starting point, if you will. It's a common, safe starting point for all of our heliophysics community, but we don't want to lock them into not doing anything else with it. We want to allow some creative freedom to add additional software or to change it as they desire. But at the end of the day, that's a safe starting point and a shareable one. And we want the community to be able to work with us on this. So right now, the Helio Cloud project is essentially simply the group at Goddard plus a group at APL led by John Vandegrift. And we've been working to develop this, but we have big ideas and big plans to involve the rest of the community. And so this presentation that I'm giving, if you will, is sort of a first reach out to the community to let you all know what we've been doing and to essentially open the door. We're very interested in working with you. So with that, maybe a little description of some of the forms that these things take. I'll have to bail out of the presentation for a minute. So here is the code repo that we have up and running. There's a link in the presentation, and you should be able to get at this. And if you can't, you can reach out to me. But essentially, and as stunning as it is to look at somebody else's code repo, so I'm not going to spend too much time here, but essentially, we've been working specifically to support the PyHC Summer School, if you've heard of it, with this environment. And we've been creating a tailored leading project to create a PyHC container. In here, you see the environment YAML file. And even better than looking at a code repository is to look at somebody's YAML file. So here is all of the projects that we currently have in, so you can inspect it. A little bit of, and this is kind of part of my my pitch to you all, is that currently many of the tools in here are only available on PyPy. And there's nothing really wrong with that. You know, in general, I'm in fact a longtime pip user myself and user of PyPy. However, the software environment that we're using that supports the containers isn't really cognizant of pip. not beyond sort of importing pip and then importing the packages. And that causes all sorts of problems in terms of full dependency resolution. I find that I have to sit down and still resolve things, quote unquote, manually. It would be much nicer if these things existed in a Conda distributable form, such as Conda Forge, and I'll get to that in a bit. Another form in which we're distributing this is the notebook container is coming out, is currently available publicly off of our Elastic Container Registry on Amazon. The plans are to sort of shift this to Docker Hub in the future, but you know, many things to do, we'll get there. But that, you know, it is publicly available now. This is, I think the link is also available there. So you can actually pull the current container that's supporting the PyHC Summer School from this environment. And I can give a demo of this later if there's time, but in the interest of time and getting through the good stuff, the main part of this, I'm going to switch back to the presentation here. So with that, so here's the next slide. Okay, and so this is just a little screenshot of what you see. Essentially, the platform that we're using here is Jupyter Lab, which is sitting on top of Jupyter Hub, which is deployed in the cloud. And then we're doing the modifications necessary to make sure that the default software environment is this heliophysics Python environment. In other words, primarily PyHC software. But our intention is to go beyond Python, just to be fully revealing of our plans. So a list of languages that we want to support or are supporting. We're currently only supporting Python, IDL, and Fortran. The IDL support is partial. We have also working with our APL colleagues to improve SolarSoft and a few other packages. And I think that's probably ongoing for some time to make them work with the cloud better. But that's part of it. So integration with other containers from our community modeling center folks. This environment integrates with very large data volumes. So our plans are by fiscal 25 to have about 8 petabytes of heliophysics research data from NASA in the environment. I think you'll agree that that would be a very strong driver and an enabler of doing big data science research. These, of course, people would work in terms of either using a Unix-like terminal or in terms of Python notebooks or other types of notebooks, which would be shareable. This environment integrates Python library called Dask, or a set of libraries called Dask. And what that does is it enables bursting into the cloud. So the virtual machine and container environment that the user gets to run into to program in is not very big, not very aggressive. But with the bursting capability, you can burst into virtually an unlimited array of machines, only limited by your financing, into the cloud. And so you can essentially farm out and do very ambitious jobs on a very large amount of data. So this is the idea here is to democratize big data and large data scientific computing for our community. Here to now, only a favored few who have access to institutional resources, including the large data volumes plus the high-end compute, could actually unlock this kind of science. And so this is very much intentional to democratize this, make this available to our broader community. Of course, by making this browser-based, no special software required, you really enable easier collaboration between academic industry and international partners. At least that's the way we see it from our NASA perspective, where getting partners onto NASA compute systems can sometimes require an arm and a leg and the blood from your first child. So this becomes an extremely easy way to build and maintain those scientific collaborations. So the architecture behind this, because I know y'all are software programmers and might have some interest in this, is the idea here is to have these environments deployed at each institution. So the purple box is kind of a deployable unit. And the main functional pieces, if you will, are to have this Dask Hub environment, which I was just showing you. This is the browser-based analysis environment, which then plugs into or can easily access this data storage component. So this is where from the NASA point, 8 petabytes of public data, but also private team data is available here. There's some bursting into standalone VMs, and then also supporting software development support. So this is where users might create a notebook and share it on a binder hub, would be in this blue box, or they create their own tool containers for software based off of the Helio Cloud container. So they extend it and then deploy that into a public registry that might be here as well. There may be some CI/CD type support here. I don't want to get into it unless there are real strong questions. The main point here is these green arrows, which are connecting to other Helio Cloud instances so that it becomes transparent and easy to share these data and these output products, right? So if I create a notebook that's doing some scientific analysis over here, it's registered in the blue bit that's in here, and then this one sees it, and then users using a Dask Hub here can then see that same notebook and say, oh, wow, that was easy to share, and I can get at your data. And we've really enabled a new area of heliophysics research. Well, not new. We've really enabled heliophysics research that here to now has been very difficult to do. So what are the specific benefits? So, what about me? PyHC developer, why would I do this? There's actually a lot more than this. I think, you can appreciate that once we start taking this perspective of sharing data and software projects and basing them in the cloud, then we have to start thinking about things that we haven't really thought about before, like, well, gee, how does, if somebody wants to provide me a location of data in an S3 bucket, does that impact my library, my package? Should I be supporting that? Should there be an S3 support package that we're all consuming? So that's one driver. If we want to move into this paradigm, and I'm going to say right now we should, or this is the future, folks, of where we need to be. This is a driver for additional development and functionality in our packages, that alone. But better than that, when we have this concept of a shared software environment for PyHC, it really enables us to take a continuous integration approach. That is, Sean or Julie could host a CI server and pull from everybody's repo anytime there's a change. Unit tests are executed. We can also analyze for dependency conflicts. We can also, it's not on here, but we can analyze for license conflicts. Is everybody totally using a public license? Are there supporting software that they're using a supporting license? There's automated tooling for all of this. There's automated tooling that sits in the CI level that we could purchase that will investigate for critical CVEs. So we can also improve the security of all of our software by taking this CI approach. There's just so much goodness here. And we can do all of this before we distribute it. We can start taking an intention of having maybe a 6-month release cycle or something like that, so that we can start getting into the mode of having development branches that we work out all of these dependency conflicts and really take a true system software engineering approach to PyHC, so that at the end of the day, our users see a better product. It's going to be safer. It's going to work better together. We're not going to be stepping on each other's toes in terms of the kind of dependencies that are available there. We won't always be able to resolve all the conflicts, but at least we can note where they exist, and we can document that for our community. This is going to improve the quality as a whole. And then there's sort of the open science take on this. Open science can be succinctly described as reproducible and transparent science. So when we create a cohesive whole that can be used for the majority of the heliophysics Python community, something that just works, you're going to accelerate the adoption of PyHC because they know that there is a one-stop shop where they can go and get basic functionality to do Python heliophysics research. Granted that not everybody, and in fact, because we still are working within our various domains, I'm an ITM person or I'm a solar person, et cetera. So you don't use all the packages, and I'm not saying that our community is going to start using all of the PyHC packages, but there are some packages which overlap in domain. And having that just work and not forcing our users to repeatedly do the engineering to make it work is going to create that better product that's going to be more reproducible. And by having this CI approach, we can tag and label it. By having these containers, here's the open science part, you can start publishing your models against that environment, right? So every 6 months, we're releasing a blessed environment. It has an official tag. It should get a DOI. And people can publish against that, right? They can write their notebooks, their model pipeline, their model software, their analysis software, their pipelines, and they can say it implements version X whatever of the PyHC shared software environment. And we publish that and they can link to that. That's fantastic. So I don't have that little line item on there, but that's what that is about. So how are we going to do this? So as I pointed out, we can't use pip. The requirements.txt file just isn't going to cut it because of the supporting software to build the containers. It requires Anaconda or a Conda environment. So I'm trying to motivate you all to consider creating either a channel on for PyHC community. That might be one way to do it, or simply we can use Conda Forge channel. The Conda Forge channel is a public channel that is, sort of a one-stop shop for the community contributed software, if you will. And it is curated in the sense that all packages are, there's care taken to make sure all the packages are up to date, that there are common standards enforced, and they auto-generate packages for Mac OS, Linux 64-bit, and Windows 64-bit. The formulation there, which I'm not going to get into, is that they sort of have a process whereby they onboard maintainers and have multiple maintainers supporting packages. So we could subscribe and do things there, or we could just go our own way and create our own channel. So I sort of leave that as a discussion point about how we approach that. So in terms of the integration and adoption, of course, there's the consideration that I just raised of, what channel and how might we approach deploying things for a shared Conda environment. I think first and foremost, we need to create a PyHC project. If the Helio Cloud project that we have going could be adopted into PyHC, that works. Or we could, skipping to the last point here, maybe it needs to be rebranded. Maybe Helio Cloud is a little too cloudy of a name because these things don't just run in the cloud, for example. So that's a slight misnomer. Maybe it needs to have a different name. But after that consideration, then that should be a public repo and it should be in PyHC. And then that would be a sort of a bonding place where all of the PyHC projects, which are going to be under support for the shared environment, could be discreetly laid out. And if we have system unit tests, then they go there. We would start and have started with core packages plus a few others are currently under support. And we would also want to, as part of this CI environment, push out the container build Docker containers and push them out. So we can also do that. There might be some kind of threshold to inclusion. So projects which have really gnarly third-party dependencies that are in conflict would probably not go into the system container to start. There might be some resolution or discussion in the community on how to do that. And then there's no requirement that you have to be part of it. But I think as we go along here and we see the value in doing this, I think that there's a real carrot to members of the PyHC community in being included. I think that's my last slide. Here's the last slide. So the existing work that sort of bears on this discussion is laid out here. There's actually needs to be updated. This is PyHC now, but this is good enough for this sake of this presentation. Yeah, so that's that. I'm gonna cut my presentation short right there, see if there are any questions. And if people are looking for more punishment, I can give a demo of the DASCUB environment.
There was one question in the chat. about AWS?
Yeah, no, and the answer is yes, because we use the commercial AD. So the short answer is yes. It's very easy to access, and it doesn't have the usual NASA IT constraints. There's a security plan around commercial cloud that NASA has, and because of the way it's engineered, we don't have the PIV requirements, although we do require two-factor. We can onboard scientists who are partnering with NASA researchers or have NASA grants from basically anywhere in the world.
Can I ask who pays for the AWS instances, and are there any constraints on that?
So the idea is that each of the partner institutions would pay for their own AWS environment, but because these environments have shared standards and registries of the data, then the minute that you bring up yours and your team starts hosting public data, it becomes registered with all of them. And because the cloud, even though your institution might be in Colorado or in Europe somewhere, it's in the cloud. So it's more or less as close to somebody else as to someone else. That's not entirely true, and I don't want to dive into that wormhole, but that's the idea. So if you publish things, then it just accelerates the adoption of your public data or the utility of your public data to others who are also in this environment. And of course, you don't have to be in this environment. The minute you put it in the cloud, others can use it if they're very easily if they're in the cloud. It's just that by having Helio Cloud instances, then there's a facility for co-registering and making sure the registry is up to date between these instances. It's more discoverable. That's the primary motivation.
Oh, thanks. This is really interesting. One other question is, would we be able to use this environment for, say, PyHC tutorials after the summer school? Like I'm going to be one for RU students. So, okay, cool.
Yeah. Well, the PyHC summer school environment is hosted on NASA resources. We intend to spin that down, but whatever products are produced should work in that environment. And we can talk further offline about what that looks like. If there's a desire to continue to have a live environment, I think at the very least, having a shared binder hub for the PyHC projects in some fashion is desirable, or just post them on binder. I'll have to think about that more, but I think there are ways to do this.
All right, thanks.
If I can ask another question, then you mentioned pip not being ideal. I've no experience with setting things up for Conda. Do you or anybody else here? Can you comment on how easy it is to take a repo that's currently on GitHub and converting that so that it's accessible from Conda?
It's pretty straightforward. The formulation looks the same as the requirements.txt file. More or less. I think there's a dash instead of just putting it on the line, but I think everybody can handle that. And you just say equals this version or greater than equal to this version. I think the main thing is getting the channels right. The default channel often doesn't have the dependencies that you need to pull, and you have to put it in the Conda Forge channel. And then of course you immediately run into issues with, if you're depending on other PyHC packages and they're not in Conda, then you have to do the little trick that I showed where you include pip as a dependency and then you show what runs under pip, and it'll pull it from PyPy. The problem is that when you go to create a lock file to sort of lock in all the dependencies to make sure that it's stable, the Conda lock will immediately tell you that it can't handle pip dependencies. So that's kind of a more in the weeds reason. And so then it really doesn't get, you didn't have the problem of, well, first of all, Conda lock won't include anything that's a pip dependency. And then you have to go back and you have to rerun a specialized requirements file with all the locked versions. And it also won't figure out the interdependencies between the things that are in PIP and the things that are in Conda. So there could still be a third-party dependency conflict, and that's a pain. So that's the bit that I've been having to work out manually. So, you know, I don't want to make it sound like I'm whinging or anything, but it would make my life a whole lot easier if you guys were all on Conda, and I wouldn't have to sit down and manually figure out your dependency conflicts. So I think that, you know, that's how when I first sat down to do this, and Julie said, well, would you like to give a talk on this? I thought that I would take that perspective, and it's still true, but I'm trying to sell you guys on the larger benefits of doing this, from having a shared software environment where all the engineering is done up front and that our users don't have to do it. Again, being able to understand up front any of the dependency conflicts is a big one. Being able to see that you have any security problems and fixing that, or at least flagging that, is a good thing too. Being able to have an extensible environment that we can distribute out to users so it just works, and that they can build on top of that and they can publish against it. That's big too, right? So moving into this is a first and necessary condition, I would argue, for us to, number one, moved into shared environments, which are going to be necessary for cloud-based computing and arguably for any kind of shared platform computing. And number two, to support open science in terms of being able to publish in a reproducible and transparent way. We need to support software for research in open science. And the best way, I would argue, in a first and necessary condition, is to create these shared environments, which we can tag and publish out, put DOIs on, and people can reference, right? And so years from now, when somebody wants to run a model that was developed in 2022, they're going to be able to do that, or they're going to have a much better shot of doing it than today, when I tried to run something that was written in 2006, as recent as that, although I guess for the young members of this community, that sounds like ancient times, but that can be a problem. Right? It's not trivial to do something that old, which doesn't seem that old to me. Nevertheless, trying to run something that was developed in 1992, even harder, right? So by building these containers and distributing them, we have a much better shot at the community downstream years from now being able to run and execute and inspect these models and this software. So it's enhanced value and support for open science. Sorry, I know that's all a repeat. I feel like I've stood on my soapbox, I pulled off my shoe, and I'm banging it on the desk. But that's how passionate I feel about all this.
That passion is highly welcome.
All right, well, I feel like I've stunned everybody into submission, or they're just bored to tears. But if you want to reach out to me, feel free. And I'd be very happy to talk your ear off on the value of this.
John, you had a question in the chat, right?
Yeah, I can talk to Brian offline about that one, but I wondered too about, you know, because we're working with Brian on this, and as we get this environment, the cloud piece of it set up, you know, we'll be looking for other institutions who want to try it out, kick the tires. And you know, we're looking at APL to eventually get some of the APL internal IT infrastructure money to go to support something like this, so that it's always there for people. And you know, other people at other institutions might want to start thinking about it in that way too, that as we want to support this open science stuff, institutional infrastructure money should go to support that, just the way that it supports, you know, laptops and servers and, you know, disk space. So and that answers the question of who pays for this. It's like, well, it's just becoming the way infrastructure is needed.
Yeah, so around your question about security plans, we normally can't share those, but I think what we could do is talk to the infrastructure folks who engineered in the first place and get their best practices suggestions. And I know some off the top of my head. So for example, how we've engineered the roles and the accounts in the AWS environment, I think that could be exported and also suggestions about things like always using two-factor, 12 characters, special character, uppercase, lowercase, blah, 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 number in the passwords, that sort of thing, I think. But maybe the roles would be the gist of it. So we define a number of platform roles. And in fact, that's one of the things our team has been working on, John and I and the others, is trying to figure out, can we create a sort of dashboarding facility for a user self-serve facility that plus the Dask hub that is sort of going to cover most of the bases in terms of interaction, so that people don't have to directly be on the console for AWS and sort of control those permissions. So there is some security concern built into the Helio Cloud distribution that we're talking, John just mentioned, and that's exactly right. We want partner institutions to also deploy Helio Cloud. And that would kind of be, those bits would be rolled up in the Helio Cloud. So recommended roles for users on your platform. Here's also the user self-serve dashboard. Of course, you can do whatever you want, but this would sort of serve as a default and a recommendation.
Yeah, thanks.
Yep.
Great. Well, thanks again to Pete for the excellent project introduction. I was just mentioning in the chat with you that if you send me your slides, I can also send out the questions you'd had for all of us when I send notes out, so people can get back to you with that information.
Yeah, thanks. That'd be great.
Perfect. And then Brian, thanks so much for the overview on Helio Cloud. I think it's a great tool. I'm looking forward for the community to adopt it further. So, sorry, Sean, were you going to say something?
I just said same.
Oh, perfect. Our next telecon is going to be in a little over a month because we've got a few other activities going on in the meantime. We have our spring meeting next week, like I mentioned at the beginning of the telecon. I'll send out info about that in the follow-up email with notes from today. And then we also have our inaugural PyHC 2022 summer school happening at the end of this month. If you're registered, you will receive Zoom info via email. Otherwise, we will be planning to live stream our sessions to our YouTube channel. So look out for that. And I will see most, hopefully, of you next week at the spring meeting.
Thank you.